I'm Dr. Anthony Deese. I'm an assistant professor of electrical and computer engineering at the College of New Jersey. I'm also director of the NSF-funded Smart Electric Power System Laboratory at this institution. And today I'm going to be talking about smart grid technology and its relationship to energy sustainability. A copy of the article accompanying this presentation may be downloaded using either of the links shown behind me. What is sustainability? What is a sustainable energy system? It's one that consumes energy from natural resources at a rate slower than they are replenished, as well as meets current needs without compromising the ability of future generations to do so. Generally, such systems rely heavily on several renewable energy resources, operate with high efficiency, and have minimal negative impact on the environment. Well, so why is energy sustainability important in today's world, especially given the United States' recent surge in domestic energy production? Technical experts have stressed for decades the need to re-examine energy use worldwide. Since 2003, crude oil prices have more than doubled as a result of increasing demand from the United States and China, political instability in the Middle East, and a plateau in world production. Some predict that increased investment in refining facilities and extraction of petroleum from potential reserves, like the Arctic Ocean, will cause prices to drop. However, even this minority in the scientific community cannot deny that many cheap sources of oil are depleted. Outside of the Middle East, it's pretty difficult to recover large quantities of petroleum for less than $20 per barrel. Although oil production in the United States has potential to surpass the combined output of Saudi Arabia and Iraq and a lot of these Middle Eastern countries in coming years, more than 30% of the petroleum is extracted as shale oil. The shale oil extraction process is unfortunately more complex and expensive than traditional onshore drilling because it requires conversion of different organic compounds found in rock to usable fuel. The cost associated with crude oil production at traditional oil fields like the Rawat in Saudi Arabia or the Bergen in Kuwait is less than $5 per barrel. However, it can cost almost 10 times that amount, so let's say $50 per barrel, to extract shale oil from rock formations like Texas's Eagle Ford and North Dakota's Bakken. It's possible that the average cost of oil recovery will increase drastically in coming decades, mitigating any price drops resulting from increasing supply. The figure behind me illustrates that almost 40% of energy consumed in the United States is acquired from petroleum. I don't think that's any surprise. And as such, a strong correlation exists between the price of oil and that of energy in many forms. This relationship is further illustrated in the second figure. It shows that the average WTI, or Western Texas Intermediate price of crude oil, increased by less than 70% between 1993 and 2003, yet it surged by more than 300% in the following 10 years. The residential price of electricity in the U.S. followed a similar trend during that period. It remained relatively stable between 1993 and 2003, and then rose by more than 40% in those following 10 years. So we see that the effect of oil prices on the energy market has been mitigated somewhat by a recent surge in domestic natural gas production. However, even with this increased supply of fossil fuels, really domestic energy prices have continued to grow. Although increased reliance on alternative fossil fuels provides a short-term or a quick fix to sustainability problems, it doesn't address core issues that include resource variety, energy efficiency, and really the most important, renewability. And these issues are essential for long-term energy sustainability. So, are renewable energy technologies the one and only key to improve sustainability? I would argue no. That the most effective solutions are those that employ a variety of new materials, chemical processes, and electromechanical technologies to change and revolutionize the ways in which energy is converted, distributed, and consumed. Although awareness of the need to improve energy sustainability by developing new renewables and new alternative fuels is greater than ever, it's problematic that the role of traditional electric power and what we call smart grid technologies in this initiative is often understated. So the histogram behind me illustrates, and I put this data together, it illustrates the average frequency with which various energy-related topics are referenced in recent news stories. So here you have the topics that are coming up the most, and then the topics that are being referenced the least. It represents the composition of approximately 200 or so articles from mainstream organizations such as CNN and the Washington Post, and I acquired most of them from an online search using the keywords sustainable and energy. Now the results show that authors emphasize broad topics such as green technology over comprehensive discussion of issues like energy storage. Now this is an understandable strategy given their target audience. However, the degree to which renewable energy topics are emphasized over others, so let's say those related to electric power, this is almost 10 times more. So this differential is pretty questionable. Now, how may traditional electric power technologies be used to improve energy sustainability? So what are traditional electric power technologies? The ones that we use every day. The generators, transmission lines, distribution lines. So electricity is a versatile, renewable, and efficient energy medium. Unlike alternatives such as natural gas, electricity may be effectively converted to and from energy in many other forms. Albeit with varying levels of efficiency, electric power may be generated from heat and kinetic energy via electromagnetic induction. This is your good old electric generator. Chemical energy via electrochemical processes. One example is the battery. Electromagnetic radiation via photoelectric effects, temperature gradients, physical deformation of different materials, as well as radioactive decay. With regard to application, similar methods apply. Electric power may be used to drive a wide variety of mechanical, chemical, and thermodynamic loads, as well as store and manipulate information. Prime example being the digital computer. So the versatility of an energy market with increased reliance on electric power translates to lower and more stable commodity prices. This is because an operator, or whoever's in charge of your energy system, may shift generation resources in response to fuel supply changes as dictated by cost or economic dispatch. Furthermore, almost all renewable energy resources generate some combination of heat, kinetic motion, and electric current. Although these renewable outputs may be used to drive on-site loads, really conversion to electricity is required to distribute or give this energy to any customers that are off-site or not located right there. This point is important because renewable energy resources are most abundant in low population areas, far from the urban load centers with high demand. For example, New Mexico receives solar radiation with an intensity almost 40% higher of any state within 500 miles of New York City. However, its population density is fifth lowest in the contiguous United States. The map behind me illustrates that electric power transmission and distribution capability is essential for greater penetration of renewable energy resources. We need to get the solar energy from here to here, as well as here, here, and other high population areas. A number of parallels exist between the distribution of energy to customers as electric power and fossil fuel. The energy flow diagram I displayed earlier shows that both deliver energy to customers with an average efficiency close to 40%, taking into account all end users. However, there are two important observations that we need to make. First, these numbers don't consider the energy that's used to fuel the tankers, trains, and trucks that transport fossil fuels. And then second, the efficiency of petroleum resources used as gasoline and cars is significantly lower than any alternative, including electricity. Now, although I'm not going to discuss it in depth, the table behind me predicts that overall energy efficiency in the U.S. could be increased by more than 1% by greater reliance on electric and plug-in hybrid vehicles. This may not seem like a lot, but it's approximately 293 terawatt hours per year. This is almost 70 times the annual output of the Hoover Dam. So since we're talking about electricity, I would like to discuss the question that's displayed behind me. What are some of the main limitations of today's electric power technologies? Although the electric power grid is an efficient and reliable tool for conversion and transmission of energy, it's not without need for improvement. Now, the current system differs little, arguably, from the design published by the famous Nikola Tesla in 1888, relying on aging technologies and what most people will call less than optimal operating techniques, such as, we're going to go through these that are written right here. One primary one is demand-driven generation and control. Because power systems traditionally have little energy storage capability, they must be operated such that the aggregate output of all generators meets network demand as it changes in real time. Now, what this means is whenever you turn on your light in your bedroom, somewhere there's a generator that has to put out a little bit more power. This is referred to as demand-driven generation or demand-driven control. Although the United States power grid generates more than 1,000 gigawatts of electricity to meet its peak demand, or the demand at the highest point, its total instantaneous storage capacity is less than 50 gigawatts. The traditional approach to bulk storage, so when I talk about bulk storage we mean more than 1 megawatt hour, is mechanical, because technologies like pumped storage hydroelectric, one example shown behind me, and compressed air turbine generation are more cost-effective on larger scales. Still, their use is often limited by the need for specific geological conditions, again, example here, and site development. For example, a significant elevation gradient is required to effectively implement pumped storage hydroelectric. Other methods to store electric power, such as electrical, the capacitor, electrochemical, and the battery. Now they're well suited for small-scale applications like transportation and portable electronics. However, as illustrated by the table and then the calculations behind me, their low energy density and relatively high cost make application to grid-connected or bulk storage impractical, at least with today's technology. Another limitation that we're going to discuss is the stochastic nature of load behavior. Because loads are monitored and controlled predominantly by the customer, they exhibit unpredictable behavior that must be modeled stochastically. As such, a network operator has limited information regarding current as well as future demand. A complex analysis known as load forecasting is used to predict demand from historical trends, weather data, and knowledge of special events like concerts or holidays. Forecasts may be divided into three categories by length: short term, which is about 1 hour to 1 week, medium, 1 week to 1 year, and long term, which will be greater than 1 year. Generally, the expected error of a forecast increases with its length. I mean, this makes sense. It's harder to predict something as it's further away, with many commercial operators able to estimate day-ahead load profiles with an accuracy of 97 to 99%. Pretty good. A number of statistical techniques and artificial intelligence algorithms are applied to load forecasting, including nonlinear regression, artificial neural networks, and fuzzy logic. Next is spinning reserve, or more appropriately, the need for spinning reserve. Because power systems exhibit unpredictable behavior, a balance between supply and demand can't be maintained by traditional generators alone. And so what I mean by traditional generators is one that's set to output a certain number of megawatts and it remains static. Other units with the ability to quickly increase and decrease their real power output via fuel throttle control are referred to as spinning reserve. These units must be dispatched to account for unpredictable changes in network supply as well as demand, resulting from customer actions, weather, and let's say things like network faults. However, it's advantageous to minimize reliance on spinning reserve units because, on average, they're less efficient and more expensive to operate than their traditional counterparts. Economic dispatch analysis is used to determine the optimal output of multiple generating units within a power system, and what we consider as parameters such as fuel cost, efficiency, and then the physical constraints of the power system itself. So another issue we're going to discuss is centralized generation. What is centralized generation and why does it limit power system performance? Traditionally, electric power grids employ this centralized generation scheme, one in which a small number of large units supply almost all the power consumed by industrial, commercial, and residential loads in an area. This topology, which is illustrated on the screen behind me, emerged in the early 20th century because a large generating unit, especially one that burns fossil fuel, was cheaper to develop and operate than several smaller facilities with the equivalent aggregate output. Several benefits existed, including proximity of resources. So the cost associated with transporting fuels and materials like coal was significantly greater than the cost associated with transmitting electricity in the early 20th century. Therefore, it was often advantageous to develop generating units in places where sufficient resources exist, even if it meant that we had to build expensive transmission upgrades to fit that generator. It was better to transport electricity over long distances rather than fuel and water. I guess they're heavier, so it makes sense. Another benefit is greater generation efficiency. The efficiency of a turbine, and this still stands today, is maximum when steam is expanded in stages. So as such, large and more complex generating units were better able to recover heat, and they exhibited greater efficiency than smaller units. Another issue is manpower and overhead. So large generating units take advantage of economies of scale. As such, the manpower and overhead costs associated with one generating unit were less than those associated with several small. For most of the 20th century, as utilities strive to meet the rapidly growing demand for electric power, development and construction of new generating facilities outpaced transmission and distribution network expansion. This is because the former, generation, has a more direct impact on available power supply, as well as being less costly. Because of this policy, or this way of operating, modern transmission and distribution networks, and we're talking about today, are increasingly stressed and less able to efficiently transmit power from centralized generating units to load centers over long distances. Additionally, in a centralized generation scheme, the average distance between generator and load is large or long, yet the number of transmission paths between them is small. So there's not too many paths to go from generator to load. In a centralized generation scheme, the detrimental or negative effect of a single event like a line fault, lightning striking something, the detrimental effect on system stability is significant. In a highly stressed network, one unlucky event can interrupt service for millions of customers. The 2003 Northeast blackout was ultimately caused by some untrimmed trees falling on a line in Ohio. Another limitation of today's electric power technology is the need for synchronization. So because power grids in the U.S. transmit electricity as 60 Hz alternating current or AC, separate subsystems can't be interconnected without synchronizing them first. The difficulties associated with synchronization discourage network operators from opening switches to divide a large system into smaller pieces, even when islanding, as this process is referred to, may prevent the spread of cascading voltage collapse or just improve overall system performance. Now, going back to the 2003 Northeast blackout, Philadelphia and southern New Jersey were only spared because operators islanded our network from neighbors to the north. Any mismatch between supply and demand within a power system will be reflected in the frequency of the AC waveforms in it, as well as the angular velocity of its synchronous machines. In short, these mismatches cause generators and machines to speed up or slow down, and if unchecked, these changes may result in a blackout. Another issue is the complexity of nonlinear system analysis. Because a power system exhibits nonlinear behavior, basic linear circuit analysis techniques like nodal and mesh analysis, and these are the type of techniques I teach in my ENG 212 class. Now, they can't be effectively applied to a power system. For advanced power system analyses like load flow or state estimation, iterative numerical methods are generally employed. One example is the Newton-Raphson. However, even when implemented via digital simulation, the complexity of and time required to complete these calculations increase drastically with system size. In short, it's much more difficult to perform analysis on a 200 bus system than it is 100 bus system. As a result, power system size is a significant constraint when it comes to calculation. Now, with regard to the last two elements here, unidirectional power distribution and less than optimal control. So traditionally, power distribution systems, which are really the lower voltage version of a transmission system, employ a radial feeder structure in which power flows unidirectionally from a substation to all the loads. The assumption of unidirectional power flow makes distribution systems less expensive as well as less complex to design and operate, and this allows the use of simpler measurement, analysis, and control techniques. However, the increased penetration of energy from distributed generating units, and this includes renewables, will affect the predictability of flow within these distribution networks and eventually, if not sooner rather than later, require adoption of techniques that consider bidirectional flows. And then lastly, less than optimal control. So we kind of hinted at this before. Traditionally, power grids are operated in a conservative manner, with maximization of reliability and minimization of controls held paramount. So the big concern is, how can we just keep the system running stably and keep the lights on? This mentality may be attributed to the lack of customer tolerance for even short and localized interruptions of electricity service, as well as the time and effort required to perform manual hardware actuation on which many utilities still rely. Furthermore, operators often lack the measurement and computation capabilities required to address issues such as efficiency and renewability via closed-loop control in real time. My list provides really only an overview of the limitations exhibited by modern electric power technology, and a large number of more complex issues exist. For example, in a deregulated environment or a deregulated electricity market, it facilitates trading of electricity between participants as well as delivery to customers over short and long term as dictated by spot and forward prices respectively. Because the spot market considers real-time transmission network congestion and geographical distribution of demand via what's called locational marginal pricing, or LMP, the resulting equilibrium can be unpredictable. And so retailers supply electricity to customers via purchase of resources from spot as well as forward markets. They must constantly reevaluate the composition and diversity of their energy portfolio to minimize risks associated with potential spikes or dips in LNP, as well as long-term purchasing commitments. So, we know that today's electric power systems are less than perfect. However, what about the future of this technology? Now that question leads me to the next thing we're going to discuss, which is smart grids. So, what exactly is a smart grid? In basic terms, it's a power system embedded with modern technology to facilitate remote hardware measurement, communication, actuation, as well as improve network efficiency, reliability, and overall sustainability. The figure behind me illustrates how technologies like digital sensing and actuation, distributed generation, demand response enabled loads, and a whole bunch of others which we are going to discuss, may improve power system performance through closed loop control methods. Now, in the United States, smart grid policy is defined by Title 42 of the United States Code, and don't worry, I'm not going to recite the whole thing. It defines a set of objectives including increased use of digital information controls technology, dynamic optimization of grid operations, and a whole bunch of very interesting sounding things. So, what are some smart grid technologies? The one that we really have to discuss first and foremost is digital sensing, actuation, and two-way communication. Now, these technologies facilitate measurement of power system voltages and current flows, remote control of components like switches and capacitors, as well as fast and reliable transmission of data between the network and the operator. Because digital sensors with two-way communication capability provide a more detailed description of system behavior, they simplify load flow analysis and state estimation, as well as allow the use of more effective operating techniques that generate better control recommendations. With remote actuation capability, these actuations may be physically applied in real time. This is a stark contrast to the way things are often done now, where you send a technician into a truck, he drives out to the switch, and then manually throws it. Another relevant technology is distributed generation. A distributed generation scheme relies on a large number of smaller generating units present throughout the network topology. So let's bring up our graphic from before depicting a centralized generation scheme. Again, the L's represent customers or loads, and we have one large generator supplying all of the loads, or a large majority of the loads. The average distance between a generator and load is high, and there are several critical lines that, if lost, may seriously affect operation. Now let's compare that to a more distributed generation scheme. The number of paths between generator and load is greater, yet their average length is shorter. This reduces network stress, improving system efficiency because less current flows along lines with smaller equivalent resistances. Reliability because fewer critical transmission paths exist. Other benefits include increased penetration of renewable energy and storage technologies. Many small yet effective implementations of renewable and energy storage technologies exist, and this motivates power system planners to consider a more distributed approach to their placement. One last benefit is increased customer market participation. In a distributed generation scheme, like the one we've been discussing, customers have greater motivation to participate in the electricity market via ownership and operation of small generating units. This participation is good because it provides customers an opportunity to mitigate their own energy expenditures via generation, as well as it introduces them to similar concepts, which we'll discuss in a second, such as demand response. Furthermore, aside from motivation, there are several key technological advances that have motivated system planners and operators to employ more distributed generation. So essentially, the technology has gotten better. Now, these technologies include power electronics. Unlike traditional generating units, many distributed energy resources are connected to the grid via a power electronic converter. So voltage source converters and maximum point power trackers are employed for grid integration of DC sources like photovoltaics, as well as variable speed AC sources that include wind turbines as well as gas-powered microturbines. The availability of cheap and more efficient power electronics make the use of a distributed generation scheme more practical than in the past. Another technology is really just better small generation technology itself. Today, a small generating unit with, let's say, between 3 kilowatts and 10 megawatt rated output is significantly cheaper, easier to operate, and more efficient than its early 20th century predecessor. This may be attributed to the availability of new fuels and metal alloys, advances in turbine, reciprocating engine, and synchronous machine design, as well as digital technology for remote control and closed-loop automation. A power system that relies heavily on short-distance, low-voltage distribution of electricity from predominantly distributed resources is known as a microgrid. So this is a topic that's very closely related to the area of distributed generation. A microgrid is a power grid that relies predominantly on this distributed generation scheme. The greatest technical challenge associated with this type of system, a microgrid, is effective management of generators and loads to ensure, what we discussed before, the balance of power supply and demand. Because microgrids are inherently smaller than traditional power systems, their generation and load profiles exhibit greater variation with time and are more susceptible to instability from sudden changes in the status of any single device. So essentially, because the system's smaller, we really have less leeway and the system is less able to tolerate deviation or difference between supply and demand. Although microgrid topologies are not often used in more urban, let's say first world areas, they are the backbone of many energy systems in, again, more rural, third world areas, and one prime example is American military installations or American military bases. Now, going back to some of the relevant smart grid technologies, one that we have to mention, or one very important technology, is grid-connected energy storage. Emerging technologies such as the hydrogen fuel cell, supercapacitor, and flow battery have potential to facilitate increased energy storage within electric power grids. They may be configured to maintain the real-time balance between generation and demand, this balance that's essential to power system stability, and yield an alternative to spinning reserve and frequency regulating generators that is both potentially cheaper as well as more efficient. Also, because many of these technologies may be actuated remotely, they allow operators to use more robust or better control schemes and more effectively dispatch renewable energy resources. In short, energy storage capability improves power system performance by alleviating the need for demand-driven power generation. Although I'm not going to discuss this figure behind me in detail, it does outline the characteristics of several electric power storage technologies, focusing on discharge time, how quickly they may supply energy to meet load, and size in terms of power rating or megawatts. One of the most promising technologies is the flow battery because it may be potentially applied to both small-scale and large-scale storage. Now, another very interesting technology, I think probably the most interesting that we're going to discuss, is demand response. So the term demand response describes a practice or techniques which influence the consumption patterns of the electric power customer. Influence that may be expressed directly, so this would be the system operator having the ability to control loads within the home, or indirectly, where the system operator may manipulate energy prices and encourage the homeowner or the customer to make changes to their electricity use. This technology partially reverses the demand-driven generation model to a generation-driven demand model. The question is, if done effectively, will customers be willing to sacrifice some comfort and control over their own devices for what I like to call the greater good? Now, with regard to demand response, what are some objectives that we have? One primary is cost minimization. So demand response may be utilized to increase or decrease the consumption of individual loads on the basis of actual or projected electricity costs. The objective would be to operate non-essential loads that perform time-insensitive tasks. So one prime example I always use is the washing machine, running that late at night. So to perform these time-insensitive tasks when electricity prices are low, providing customers with an opportunity to reduce their average billing rate in dollars or cents per kilowatt hour. Another objective is reduction of peak demand. Similarly, coordinated demand response. So we're talking about demand response of a lot of homes over different neighborhoods or even multiple towns. So this coordinated demand response may be used to shift operation of non-essential loads from peak to off-peak hours. This reduces transmission and distribution network stresses, as well as improves power system efficiency and reliability. It lessens the dispatch of lossy and expensive peak generating units, as well as reduces the effect of any one component failure on system stability. One last objective of demand response is the creation of what we call a virtual generator. So demand response may be utilized to counteract the stochastic or unpredictable effects of customer action or renewable energy resources. So this discussion of renewable energy is pretty key here. The objective is to create a virtual generator, or a collection of devices for which the real power demand, which may be thought of as negative generation, is constant and available for dispatch. Available for dispatch means that a power system operator can control. This improves power system performance in many respects, serving as a better alternative to the more lossy and expensive peak generating and spinning reserve units. So the creation of virtual generation really drastically improves the practical viability of using renewable energy or renewable resources to generate energy. Now, one important question is, can fluctuating output of renewable energy resources be balanced by effective demand response? Demand response technology provides customers with another opportunity, and this is again a recurring theme, another opportunity to participate in the energy market. For example, and this is a little bit more detailed of an explanation that I kind of hinted at before, a washing machine with demand response capability may monitor local electricity prices using internet connection and activate only when they fall below a user-defined threshold. By supplying the hardware with a relatively low threshold, the user places emphasis on monetary savings over speed. A higher threshold would indicate the opposite. Because this technology may be used to manipulate the balance between generation and demand in a power system, it contributes to improved power system performance in many of the ways as energy storage. Now, another technology associated with smart grids that we're going to discuss is flexible AC transmission system technology, or FACS. So FACS technology describes the use of high voltage power electronics to provide operators with increased control and automation capability over network voltages, currents, and power factors. Generally, it's implemented via placement of controllable voltage and current sources referred to as compensators. One popular design is the static VAR compensator, or the SVC. The SVC utilizes closed-loop control of internal thyristor switching frequencies, a lot of technical stuff there, but it uses these switching frequencies to vary its equivalent reactance and perform real-time power factor correction. For all those ECE majors out there, I'm sure you know reactance is the imaginary portion of impedance. So FACS technology provides operators with greater control over transmission and distribution power flow, and really, on a deeper level, it allows shaping and or linearization of components' behavior for improved control. Again, any of the engineers watching, anytime you can linearize the behavior of a component, it's normally a good thing. Now, another technology that we're going to discuss is HVDC, or high voltage direct current transmission. HVDC technology describes the use of advanced power electronics, again, recurring theme, to link two multi-phase AC systems with a high voltage direct current transmission line. At one end of the HVDC transmission line is a power electronic rectifier, obviously with the appropriate filters. It converts the three-phase AC power supplied by network A to single-phase DC at a higher voltage. This power may be transmitted over longer distances with greater efficiency as compared to the lower voltage AC. And at the other end of the HVDC line, a power electronic inverter converts the single-phase DC to three-phase AC. This power is then supplied to network B, or the other network. These power electronic devices use high-frequency switching to manipulate voltage levels as well as shape the voltage and current wave. Now, this type of link is advantageous for several reasons, including one main one is reduced current flow. Both high voltage and direct current techniques individually, either high voltage or DC, both of them improve transmission efficiency by minimizing current flow along lines. This is important because real power loss is proportional to line current squared, as defined by good old P equals I squared R. Another advantage of HVDC is controllable power flow. The direction and level of power flow between sending and receiving end of an HVDC link is fully controllable and unaffected by most events occurring within the adjacent AC networks. And then finally, another advantage of HVDC is asynchronous operation. If you remember before, we talked about one of the limitations of current power networks or grids being the need for synchronization. So because waveform frequency and phase have no role in DC transmission, it's not required that the AC networks on either side of the HV-DC link operate synchronously. DC links can prevent transfer of fault-related oscillations, and as such, in certain cases, fight against cascading outages or blackouts. HV-DC technology plays an important role in the efficient and reliable transmission of electric power, especially over longer distances. It may be used to effectively supply urban load centers like New York City with energy from renewable resources abundant in remote areas like the Midwest. And you see this technology directly applies to that map that we talked about, whatever it was, 15, 20 minutes ago, showing how we have the most renewable energy resources in areas that unfortunately can be far from where we need them. Now, the final two smart grid technologies that we're going to discuss are related to transformers and optimal control. So, what is the underload tap changing or ULTC transformer? Distributed generators often negatively affect power quality because their output can change unpredictably with time. They don't operate with the same level of stability as larger generators. And this causes voltage at the host buses to deviate from its optimal value. Now, recent advances in ULTC technology facilitate real-time voltage regulation. Okay, so that would be essentially detecting when the voltage goes down to 95% of what it's supposed to be and bringing it back up to 100. So it facilitates real-time voltage regulation via tap changing of an energized or powered-on transformer in the face of variable supply or demand. And then lastly, we're going to talk about more innovative nonlinear optimization techniques. The greatest characteristic of a smart grid is the potential that it provides for optimal routing of power flow within a transmission as well as a distribution network. Advances in nonlinear system analysis, such as finding solutions via artificial neural networks or genetic-based algorithms, may allow operators to solve load flow and state estimation problems with increased speed and accuracy, motivating the industry to utilize optimal power flow results for smart, real-time control. Now, how may smart grid technologies address the limitations of what we have today, our traditional power systems, as well as, and it's important to go back to our first question, improve energy sustainability? Now, there are several problems with an unbalanced approach to energy sustainability. And what I mean by unbalanced is one that emphasizes the importance of renewable energy, which I don't doubt is very important. So one that emphasizes the importance of renewable energy but neglects the role of electric power in smart grid technologies. Mainly, this type of unbalanced approach doesn't consider the need to convert and distribute energy, the intermittency of renewable energy supplies, the geographical distance between renewable energy resources and load centers, as well as the temporal or time-related disparity between peak renewable generation and peak load. The times of peak generation from renewable resources rarely coincide with those of peak consumer demand. For example, wind turbines generate maximum output on average during the late night and early morning when really load is minimal, and this kind of makes sense. We really don't use too much power at night. However, the demand for electric power, now it generally peaks between 12 p.m. and 8 p.m. on weekdays. So a power system with embedded energy storage like flywheels and hydrogen fuel cells promotes sustainability because it allows renewable energy to be used where and when it's most needed. Now, another issue that we have to discuss is bulk storage for transportation. Without effective techniques for bulk storage of renewable energy, the application of renewable energy resources to things like transportation is difficult. Aside from biofuels, all other forms of renewable energy require storage in an electric, electrochemical, or electromechanical form. Now, the growing popularity of plug-in and hybrid vehicles demonstrates that conversion of renewable energy to electricity is essential for the development of more sustainable transportation and then, again, overall energy systems. Another issue is market stability. New electric power and smart grid technologies have potential to facilitate society's transition from what we have today, which is really a fossil fuel-based energy economy, to one with hopefully a much greater dependence on electricity and renewable energy resources. And so gradual integration of renewable power into the grid with proven and reliable market practices minimizes the probability of price instabilities resulting from efforts to improve its sustainability. So essentially what we mean there is, as opposed to trying to build Rome in a day, we can slowly integrate renewable energy resources into our electric power system, which we already know is reliable, it works well, and furthermore, it has a pricing and a market structure that is stable. By doing that changeover gradually, we can increase the probability that it's a smooth transition. Now, the need for smart grid technologies within a power system only intensifies with its reliance on renewable energy. And I think that's kind of been demonstrated, in the talk, what we've said so far. As demonstrated, previously, they may more effectively regulate the balance of power supply and demand within a network, reduce reliance on spinning reserve, and alleviate the need for synchronization between generating units. They may mitigate many of the negative effects associated with the intermittent supply of renewable energy resources, including the potential for network instability or blackouts and short-term market volatility. Smart grid technologies are essential to energy sustainability because they improve overall system efficiency and reliability, as well as facilitate maximum penetration of renewable energy. So lastly, I'd like to discuss what types of power and energy research we're doing here at TCNJ. Fortunately, we don't have that much time to go through the whole array of interesting projects we're working on. I'm just going to talk about two examples. One is the development of a smart wireless network for participation of residential and commercial loads in demand response. And the second is design and testing within the Smart Electric Power System Laboratory at TCNJ. So one vital characteristic of any smart electric power system is demand response capability, because it allows an operator to dispatch both generation and load for improved network performance. Consequently, the limited participation of commercial and residential loads in existing demand response schemes is problematic. These appliances, heating and cooling units, and personal electronics, they're not designed to accept commands from the power grid, from any external source. And although supplementary hardware may facilitate this interaction, generally such solutions are expensive, require significant installation, and lack intelligent control capability. I'm working with a team of undergraduate research assistants on an innovative solution, a cost-effective and ultra-low power meshed wireless network that facilitates communication of up to 40 sensor or actuator devices within a 10,000 square foot area. For this project, we're developing software with the ability to acquire measurement data from all wireless sensor devices, quantify correlations between input and output variables, employ machine learning with user feedback to determine the optimal system configuration, and then lastly, actually actuate hardware remotely. This innovative hardware and software will be applied to automation of residential and commercial loads for reduced energy consumption and participation in system-wide demand response initiatives. The system that we're working on, a technique, is designed to support the Zigbee Smart Energy Standard, one that's used by a whole wide variety of utilities, including Pacific Gas and Electric Company, as well as Southern California Edison. Now, this research requires a combination of commercially available and custom design hardware. The custom design hardware being developed by us. Now, the pieces include the DigiConnect Port X2. This is a commercially available RF, or radio frequency to Ethernet gateway, that facilitates communication between and networking of wireless radios and associated devices. It features an open source development environment in the Python programming language, as well as the Digi Smart Plug. So this is, again, a commercially available wireless sensor and actuator device that facilitates remote switching of loads and provides some limited observation capability. So essentially, it's a device you plug into your regular wall socket, and it allows you to turn on and off whatever's plugged into it remotely. Now, all of our hardware relies on XB Series 2 radio and Zigbee communication protocols based on the IEEE 802.15.4 standard. And it uses this to interact seamlessly with the DigiConnect Port X2 and then furthermore, the Python open source development environment. The third component of the system, which we're developing here at TCNJ, is the multi-sensor and lighting actuator. Not the best name. We're trying to think of a new one. But a block diagram of that hardware is shown behind me. And so the MSLA is a custom wireless sensor and actuator device. It facilitates remote switching of lighting loads, so those loads which aren't covered by the smart plug, as well as sensing of ambient light intensity, presence of motion, background noise, and then the voltage available at the socket. Like the smart plug, this device relies on Zigbee communication. Unfortunately, we don't have time to discuss the higher level and more theoretical aspects of the project, such as the machine learning and optimization techniques employed. However, these details will be published in coming months. In short, what we're trying to do is develop a system that learns from its customers' actions and behaviors and tries to preemptively understand or decide what loads it does or doesn't need. So the system would learn the daily actions and attempt to turn off lights that it knows that the user is not using, or turn off a television or a video game system that it knows that the user may not be using at the moment. Now, moving on to the second topic which we're going to discuss, which is the Smart Electric Power System, or SEPS laboratory here at TCNJ, which we're lucky enough to be standing in at the moment. So going back to the SEPS laboratory, now many electrical engineering programs in the United States support advanced power engineering laboratory facilities. Examples include my alma mater, Drexel University, Georgia Tech, Iowa State University, Kansas State University, Texas A&M. Unfortunately, I don't have the time to list all of them. Now, these laboratories facilitate innovative energy research, providing the ability to observe complex physical phenomena such as voltage collapse or blackout, as well as implement and test new hardware. So one example would be new types of power electronic converters. They also facilitate greater student understanding of concepts related to power system analysis, power electronics, and electric machines through hands-on learning. We're very lucky at TCNJ to have access to the Smart Electric Power System Laboratory, which again we're standing in right now. I advise the design of the facility and serve as the laboratory director. The fully reconfigurable 6-bus, 3-phase power system hardware operates with ratings of 208 volts line to line at 60 hertz and a power rating of 0.2 kilowatts. The schematic of the laboratory is shown behind me. It's composed of various synchronous generators with associated prime movers, induction motors with associated dynamometers, transformers, transmission lines, contactors and relays, constant impedance loads, renewable energy, emulator modules, battery storage, and associated power electronic converters. So, I mean, as compared to some other laboratories, it has a high level of penetration of what we talked about earlier of smart grid or emerging power technologies. The SEPS lab significantly expands upon the ability of faculty like myself and students here at TCNJ to study energy problems, providing a sound foundation for our institution's small but growing power engineering program. Now, the National Science Foundation Major Research Instrumentation, or MRI program, provided external funding for the hardware. It's also partially supported by a pending grant from the NSF's TWOS program, which stands for Transforming Undergraduate Education in Science, Technology, Engineering, and Mathematics. Quite a mouthful. Now, not many smaller colleges and universities, especially those like ours, those that focus on undergraduates, have access to power system laboratories like SEPS. Many times because of the associated costs, space requirements, and difficulty associated with custom hardware implementation. As such, we are a unique institution. We provide our students with access to the highest quality engineering facilities, as well as the opportunity to participate in advanced engineering research, hands-on work that prepares them for future graduate studies or careers in industry.